Good afternoon, everyone. My name is Neal Ford, and now I'm going to talk about building microservice architectures. This is, for those of you who saw my keynote this morning, this is an example of one of those evolutionary architectures I talked about, but I'm going to go into a lot more detail about this specific architecture today. And what I'm going to talk about this afternoon is, first of all, what problem are we trying to solve here? You shouldn't just adopt a microservice architecture because it's the new shiny cool thing on the block. It's there to solve particular sets of problems. And in fact, there are some sets of problems that it specifically is not well suited for. I'm going to talk about some of the characteristics of microservice architectures and then talk about some of the engineering practices required to make it work. One of the unique things about the microservice style of architectures is it's the first post-DevOps revolution architecture, meaning that the architecture takes all the DevOps engineering practices as part of the architecture. It's the first post-DevOps architecture, and it won't be the last one, because I think going forward, that's going to be an integral part of architecture because it gives you some unique advantages. So let's talk about what problem we're trying to solve here with microservice architectures. And I'm going to first talk about the more traditional service-oriented architecture that was all the rage, say, 5 or 6 or maybe 10 years ago. And service-oriented architecture was all about taxonomy. It was all about categorizing services and having very specific responsibilities for each layer of these services. And so I'll talk about each of these layers very briefly. At the top of this service-oriented architecture were these business services. These were abstract enterprise-level coarse-grained services owned and defined by business users. These were the abstract things that you do as a business. So for all of these things like execute, trade, or place order, the common test that you apply to those is, can you say, I am in the business of executing trade or placing order? So those are these abstract things that we want to do as a business. And frequently these have no implementation details. Sometimes they're specified in metadata formats like WSDL or XML or BPEL or something like that. The next layer of this architecture are the enterprise services. These are the things that actually implement the details of those top-level coarse-grained services. These are coarse-grained still, but these are concrete implementations, and these are owned by shared services teams. This is very frequently the land of integration architecture, so it may be that you're integrating with PeopleSoft or Oracle Financials to make some of those things happen. And these are services like create customer or calculate quote or validate trade. Then you have these application services. These are concrete application-level fine-grained services owned by application teams. These are one-off kinds of services that a particular application needs, like geolocation or search or something like that, but you don't really want to expose to all of the services in your ecosystem. So these are generally bound to a specific application context, meaning they are attached to a single application. And these are things like add driver, update address, or calculate sales tax. Next, you have infrastructure services. These are the plumbing services that are required in the architecture. This is logging and auditing and all the non-functional requirements. These are typically concrete enterprise-level fine-grained services owned by some sort of shared services or infrastructure team. And these are basically your non-functional requirements. And then finally, the defining characteristic of this style of architecture is this message bus thing in the middle, which may do 0 to all of these things: mediation and routing and choreography and orchestration and several different levels of method and message enhancement and transformation, and up to protocol transformation, transferring between serialized object and JSON and all these magical kinds of facilities. And so when you look at a service-oriented architecture, you have to ask the question now, what problem are we trying to solve with this architecture? What led us down this path? What was the advantage of having an architecture like this? And one of the advantages of this architecture is it allowed you to maximize reuse to the maximum degree. At least this was the goal in this architecture. Because what you really wanted to do is be able to build these enterprise services and then kind of stitch them together to satisfy those top-level coarse-grained services. And so there was a real desire here to maximize reuse and maximize what I call canonicality, single sources of truth for things. This is also a time when operations was more expensive and harder than it is now, because it was very common in this time that you were dealing with operating systems that had licensing for users and licensed software for database servers and application servers. And so there was a real desire to try to maximize reuse onto machinery as much as possible. So we built a lot of really elaborate shared resource kinds of architectures. The problem, though, that this kind of architecture introduced was that incremental change is hard here. If you start thinking around domain lines, like customer or orders or catalog or something like that, where does customer live in the service-oriented architecture? Well, it lives in all sorts of places here. Part of it's in these abstract pieces, part of it's in these concrete implementations. So there's no real clear defined concept of a single domain entity here. So if I want to make just a change to something in customer, I have to touch lots of moving parts. And when I touch those moving parts, I have to make sure they all get deployed together correctly. And there's a lot of operational complexity here. And this is the other downside to this style of architecture. It's very operationally complex because these different parts typically run on different machinery, whether virtualized or otherwise, and a lot of integration architecture headaches go along with that. Which brings me around to the problem we're trying to solve with microservice architectures. Microservice architectures were heavily influenced by this book I mentioned this morning, Domain-Driven Design by Eric Evans, which is ostensibly an object modeling technique, a way of taking a big complex problem and breaking it down into smaller pieces so that you can understand it more effectively. And as I mentioned this morning as well, there's a really good guide to implementing this in software by Von Vernon called Implementing Domain-Driven Design. And this idea from Domain-Driven Design that my slideshow stopped for some reason at. This idea from domain-driven design has been really, really influential on architects over the last few years. Is this bounded context idea. And in fact, that's really what the microservice architecture style is taking this logical bounded context idea and making it a physical reality using the engineering practices that we find in continuous delivery. So let's look at the characteristics of a microservice style of architecture in contrast to the service-oriented architecture we saw before. This is still a distributed architecture, like a service-oriented architecture, meaning all of these guys are living in their own processes. This API layer that you see here is purely optional, and in many diagrams you don't see that at all. This is generally just there to facilitate calling through something like a user interface to get to this constellation of services, the group of services that are running here. There is specifically no logic in that API layer. So this is nothing like that message bus that we saw before, for reasons I'll get to in a second, but you are absolutely forbidden in this architectural style in its purest form from putting any sort of logic in that API layer, and I'll show you why in just a second. Typically the communication between this API layer is something like HTTP REST or messaging over message bus, and I'll talk more about that in just a second. All of these components are completely separately deployed, and that includes the API layer at every single one of these microservice components because they're completely decoupled from one another operationally. The service components here may consist of several different classes in a hierarchy. Typically, the goal here is to have very small chunks of functionality, so you typically won't have really large hierarchies in here. You could, in fact, have a framework inside there if you had some sort of need to do some really fancy calculation or something like that. It would not be unreasonable to embed a business rules engine in one of these if it needed to handle some sort of specific task like that. The real defining characteristic of this architecture, though, is that domain-driven design bounded context idea. And this is why you never see any logic in this API layer in this architecture, because everything that pertains to a particular service is supposed to be part of that bounded context. And that may include things like databases, because the persistence is part of the bounded context, and so if you completely decouple that from everything else, you get a really, really nicely decoupled architecture. That doesn't relieve you from the responsibilities of doing things like backups and restores and all the other things that you're supposed to do with data, but what it does is remove responsibility from the databases, from the DBA group, and makes it the responsibility of the individual service teams, which frees them from choosing their own flavor of data much more effectively. But notice it's not necessarily just a database. This may be, so for example, maybe the service component we have here is a search component. And maybe that's a search engine that it needs to be able to boot up and use to be able to facilitate search. The idea of the bounded context is that operationally, when you deploy that component, all of its dependencies are deployed along with it as a single unit, because the goal here is a shared nothing kind of architecture. And I say this is shared nothing, but there is actually two things that we end up sharing here, and I'll talk about those things specifically in just a second. But from a technical architecture level, we're trying to decouple all these components as much as possible. Service orchestration in this world means that components call each other to get stuff done. There are a couple of different flavors of this, which I'll talk about a little bit later, either orchestration or choreography. But notice there is no central calling authority like a message bus here, and so these services have to call one another if they need to coordinate with one another. So when you look at monoliths versus microservices, monoliths are very much a shared resource kind of architecture. Whether you're talking about something that's in an application server or just a monolithic application in general. And the way that you scale monoliths is to get multiple monoliths together and build clustering protocols between them. The microservices world, though, is the opposite of that. The idea in the microservices world is that each service runs in its own process. And this is really because of the evolution of the way that operations has happened over time. Because back 10 years ago, operating systems were expensive commercial things you had to have licenses for, and so there was a really strong effort to get shared resource architectures to work effectively so that you could have fewer licenses to a database server or fewer licenses to an operating system. Many of you remember the days when database servers were priced by number of users, and then it was by number of CPUs, and then the power of the CPUs, and more Byzantine combinations of those things. But then something happened. This is one of those inflection points that I talked about this morning that upset the equilibrium in the software development world. Operating systems, open source operating systems, which have been free for a long time, suddenly gained a new superpower. With tools like Puppet and Chef, now you can spin them up on demand very easily and store operating systems as source code and make easy changes to them and have single sources for them. And so when operating systems are free, why not run each service in its own operating system as a single process? Because one of the headaches that you find out in a system like this is the unexpected interactions that pieces have together. And if nothing ever has an interaction with it, then you have more certainty that you're just running one thing. And if operating systems are free, then why not do that level of isolation? And now, of course, we see this down to the level of containers, running one thing per container as the representation of a pristine operating system. Another one of these perspective shifts that's quite common in the microservices world is this projects versus products perspective that I mentioned this morning. Projects tend to work in siloed organizations where you have a group of developers who hand something off to someone in operations, and then they reform and build another project somewhere else that they're going to hand off to operations. It's very easy in these organizations for blame to happen, because if something doesn't happen, well, it's that silo's problem, and there's a lot of coordination between those silos. It's much more typical in microservice architectures to have these cross-functional inverse Conway maneuver teams that I talked about this morning. Amazon's 2 pizza teams is a good exemplar of this. There's no team at Amazon bigger than 10 or 12 people, and they're all cross-functional, meaning that they own their service entirely. So they have an operations person and a DBA, and they have developers and whatever resources they need to be able to build and put their service into production, and along with a product owner. Notice that this removes a lot of the needless bureaucracy that exists in a lot of siloed organizations. When developers are trying to get things deployed and operations is stonewalling them and preventing deployments because they're trying to batch things up, All of that goes away here because every team is responsible for deploying their stuff on their own schedule because it's part of their job to deploy the things that they're building. Another common characteristic in this world are smart endpoints and dumb pipes. This is, again, this idea of message buses is not really, they don't like it in this world because what you're doing there is smearing your bounded context out across your integration architecture. So we tend not to like enterprise service buses in this kind of architecture. We like smart endpoints and dumb pipes. The typical transport here is HTTP when we get away with it because it's easy to debug. But if you need a binary for performance or because of bulk of data or something like that, lightweight message queues are commonly used here. Now, if you're in an architecture and you have an enterprise service bus, if you don't use any of the intelligence in it and just use it like a dumb pipe, then we're not mad at it anymore. The problem we have with things like enterprise service buses is that information that you're encoding in the enterprise service bus is really part of a bounded context, and you're violating that bounded context philosophy of microservices by taking some of that context and externalizing it in another moving part. We're trying to break the coupling between moving parts in the architecture here to create these shared nothing kind of architectures. And in fact, it's quite common in this world to standardize on integration and not on platform. And so it's quite common that you don't standardize on a single implementation language or even development stack. So some companies will build some of their services in Java. Google's Go language has become a very popular destination for building little tiny services because it has very few dependencies. You can build standalone executables. It has a very efficient tool chain. Now, we're not suggesting that every single development team gets to pick their own special magical development stack that no one else in your organization can possibly understand. But if you look at most large organizations and look at the spectrum of too few languages and platforms versus too many languages and platforms, most large companies fall way too far on the too few versus the too many. And so what we're trying to do is push this back more pragmatically toward a good balance for whatever your company is. My colleague Sam Newman has written a really good book from O'Reilly about microservices, and I'll give you some of his advice along the way. And here's the first bit of it from Sam, which is to standardize in the gaps between services and be flexible about what happens inside the boxes. And this is, in fact, one of the two things we do share in this style of architecture. I said it was a shared nothing architecture before, but here's one of the things that we do share, which is how the services integrate with one another. So it's quite common to pick REST level 2 or REST level 3 here as a common integration style, because what we really want out of these microservices is this kind of Lego ability of being able to pull one service out and put another one in its place, and they have to know how to integrate with one another to be able to facilitate that. And so that's one of the things that we do share in this architecture is how do services integrate with one another. And I'll talk about the other one in just a second. But Sam also says have 1, 2, or maybe 3 ways of integrating, not 20. This is not an excuse to go off and build your own special software stack. What we're trying to do here is right-size technology choices for the problem that you're facing. And he also says pick some sensible conventions and stick with them, which I think is good advice. Another common characteristic of these microservices is decentralized data management. It's very easy when you have a monolithic application architecture and a monolithic database to do transactions, but that becomes much more difficult in this microservices world. And so you typically are eventual consistency environments here rather than hardcore ACID transactional kind of environments here. And in fact, that is Sam's advice. Avoid distributed transactions if at all possible in this world. This is really one of the trickiest things, particularly if you're migrating from a monolithic architecture into something like a microservice architecture. Because one of the things that you'll find is that you have a multitude of problems around different kinds of coupling. Certainly you're aware of the kinds of afferent and efferent coupling between classes that exist within your architecture, how classes depend on one another, and the spider web of dependencies they create with one another. But that's only one of the kind of couplings you have to worry about as you transition from one architecture to another. Another one is temporal coupling, how things are transactionally tied to one another. And so if you are taking a monolith and migrating it toward a microservice architecture, the first cut should be around transactional context, not around structure. Preserve the transactional context as long as you can, and then do whatever level of distributed transactions you can get away with, or just cheat and say, okay, these three services share the same relational database because it's too hard to break that transactional context apart. You're going to end up creating way more trouble than it's worth. So it's probably better to cheat on the purity of the architecture than to try to invent some sort of distributed transaction mechanism that works across a widely disparate set of transactions. Having said that, you should try as much as possible to embrace things like eventual consistency, because a lot of these transactional problems go away if you can avoid distributed transactions and go toward eventual consistency. And you see a lot of sites do that. Even large e-commerce sites like Amazon, for example, you don't really get into a transactional context until very late into the purchasing process. Everything else is handled much more asynchronously. Another really common characteristic of microservice architectures is infrastructure automation, using things like deployment pipelines to make sure that you get as efficient a throughput in your engineering as possible to get things out into production. Deployment pipelines facilitate that by creating this kind of gated environment where you keep trying more and more sophisticated tests as your system moves through that deployment pipeline. This is also critically important in a very common pattern that exists in microservice architectures, and that is the combination of a microservice architecture and continuous deployment. In other words, as you make changes to your microservices, you want to get those into production as quickly as possible. Some of you are familiar with this document that we create at ThoughtWorks called the ThoughtWorks Technology Radar. We just finished the session on it last week in Chicago, so you'll see another radar sometime near May 1st from ThoughtWorks. But one of the things that we're talking about on our most recent radar is doing QA in production, because if you can do continuous deployment, you can actually do QA against your production rather than waiting and staging it in somewhere. And in particular, if you have things like feature toggles in place, go ahead and put that stuff into production and then just QA a branch of production that has the feature toggles turned on. That has a way less uncertainty than trying to create a production-like environment and then QAing it there and then still worrying it when it goes into production. If you can just do QA in production, that's even easier. But to be able to do that kind of stuff, you need automation, and this is what I was trying to hand-waving this morning, trying to describe. This is a really common pattern in a deployment pipeline where I'm doing continuous deployment, I have microservices, I'm making changes to some services, but I want to make sure that it works against what's currently running in production because I'm going to continuously deploy it there, but it also needs to implement the new features that I'm going to eventually want correctly as well. And so I'm testing in two different possible scenarios. That's what's referred to as a fan out in a deployment pipeline. You can do several things in parallel as efficiently as possible. If both of those tests pass in those environments to make sure that it can integrate successfully, you fan back in and then do the deployment phase as a singular thing and then get it into the actual environment so that you can do stuff with it. Having this infrastructure automation in place gives you the freedom to make changes to these services on a really rapid basis, which is quite common in this world. These microservices are small, single responsibility things, and you hear several different measures of this. You hear people say things like small enough to fit inside your head, so small that you would rewrite it over maintain it. So the idea is that if you know what a particular service, the new version of a particular service needs to do, why are you bothering opening the old one to read that? Because that's old news. Why not just crumple that up and throw it away and write the new one? If it's only 50 or 100 lines of code, why are you bothering to look at the old one to figure out what's no longer true? Just dispose of it and put the new one in place. You hear people give various ranges of lines of code, which has always been a terrible metric for anything in software. The single responsibility thing is really the thing to key on, because one of the things you'll find if you're doing this migration is, let's say that you have a monolith now and you're migrating to some sort of more service-based, like a microservice kind of thing. Single responsibility can do you really well here, because the first cut of your monolith may be a large chunk of single responsibility. So maybe you take your monolith and break it into 3 smaller things, each of which has a very broad but a single responsibility, and then take each of those things and break them into smaller pieces. And so this becomes a good guideline, regardless of how big your services are. A single responsibility and a domain focus is really a good way, a good lens to look at those through. So that's a bunch of the characteristics of this architecture. So let's talk about the problem we're trying to solve here. What does microservices give you that other architectural styles haven't? And it's this idea of being able to maximize easy evolution at the architectural level. This kind of Lego ability, take one of these guys and pull it out and pop another one in its place, and no one notices that that happened. So for a long time in software architecture, one of the ways that we defined software architecture is as the stuff that's hard to change later. And that's true in a service-oriented architecture and in a monolith and in many architectural styles, but it turns out if you build an architecture with change built into the architecture, suddenly change is not expensive anymore. That's exactly what we've done in microservices, is built an architecture where change is now not only inexpensive, but expected as part of the architecture. Now, because of this, it's operationally complex, because you have to automate all these machine creation and service discovery and logging and a bunch of stuff I'm about to talk about in engineering practices. But the real advantage you get here is you can evolve this in a really incremental kind of continuous way. So this is the first architecture where change is a first-class citizen. So I say this is the first architectural style developed post-continuous delivery. It won't be the last. I think all architecturals will take this into account going forward. Well, so let's talk about some of the benefits of this style of architecture. And here's a case study. It was done by my colleague James Lewis. Many of you are familiar with the Martin Fowler article that introduced many people to microservices. It was co-authored by my colleague James Lewis. And he did a presentation, and the paper is available, and it's also on video there on InfoQ. And this is for a banking application. This is a microservice architecture. These are the 4 applications: config, call center, marketing, and reporting. And here are some of the microservices. And I'll give you some of the details for a few of these. This configuration service had to handle 1,000 transactions per second with a 99th percentile of latency of less than 2 seconds. This is a big financial services company. This user service had to handle 100 million active customers, not 100 million concurrent customers, fortunately, but this is a large financial company. This raw transaction store service had to handle bulk loads of 30 to 90 million records every night. And so it not only had to handle that volume, but it couldn't fall over and die, because that would prevent them from getting all these records loaded. And if you're in the bank, you can't get behind on that. And so there was a really strong SLA for that. Oh, because this is financial services, the entire thing had to be PCI level 1, which is a really strict level of compliance for financial services kind of applications. But notice this is one of the real advantages of the microservice kind of architecture, because this raw transaction store, they had to build a whole bunch of really robust stuff around that to keep it alive. But because it's operationally decoupled from everything else, that didn't side effect ripple into all the other services. So each one of these services could be tuned to what we thought its volume was going to be, what level of scalability is required for that service versus the other ones. We didn't have to build those characteristics into the entire architecture and take on that extra complexity. Because these are all operationally distinct, you can build really unique characteristics at the service by service level if you need to. Another good example of a quite common pattern in this world is, let's say that you're running the Widget Co site and you need to draw the home page for widgets for your users. And you have a microservice architecture, and a user makes a request into your architecture. And so you make a request out to a bunch of services and you start a clock running. The clock is really important because you have a specific SLA to get this page drawn. And I saw the actual number for Amazon recently, but Amazon knows down to the microsecond how long they have to draw their page before an unacceptable percentage of people will get bored and wander away and buy a book somewhere else. They know exactly how long they have to get the most rich page done in the right amount of time. And so that's what the clock is for. And so, for example, one of these service calls in Widget Co may be out to give me best-selling widgets, because I'd really like to put a best-selling widgets chart on the page to let my users know what the best-selling widgets are. But I don't want to punish my users to wait for best-selling widgets if it can't come back fast enough. So another one of these calls is to the cached best-selling widgets as of 2 hours ago. And it comes back almost right away. So some of these calls come back right away, and others start coming back in a regular way. They don't display it yet. They're aggregated to get ready for display. And then eventually the clock expires, and it's time to render a display. Some of these services may try to still send stuff in, but I'm sorry, you were too late this time. I had a strict contract I had to meet. Maybe you'll get back soon enough next time so that I don't have to look at the cached best-selling widgets. I can look at the real number. The point is, I don't want to punish my user for waiting for something that they might not want. And so that's part of the strategy here. In this world, timely partial results are better than slow complete results, because I don't want to punish my users for information they don't need. And when you return here, it's typically optimized for ranking and aggregation and not necessarily for display. You can do some really magical things with highly asynchronous kinds of architectures. And while this is not strictly a microservice architecture, a good example of how asynchronicity can benefit you. Have you ever wondered how Google does that semi-magical, did you really mean this thing that they do? The way that they do that is when you make a search request, you don't make a single search request. It spawns several hundred, including common misspellings like transposed letters and misplaced vowels. And if they get really good search results back for one of your misspellings and really bad search results for everything else, they'll say, you probably meant this because I got a lot of trash back for that, what you really typed in. I think you really meant this. But think about how many searches they're doing concurrently. For every one of those, they're spinning off multiple concurrent requests, and it comes back really fast. That's this idea of building really, really highly asynchronous environments. But here's where you get to the real benefit of this architecture. One of the things that the Clojure community gave to us, besides Clojure, which is a really cool thing, the creator of Clojure is really loves words, and so he resurrected this English term back from the 1800s called complect, which means to intertwine or embrace or braid things together. And he suggests that many problems in software is where we've accidentally complected things together. And one of those, very commonly for many of you, is you have complected deployments. Because when you release components, you're also releasing that feature to your users at the same time. Well, that takes on more risk than necessary. If you could separate those two things, you would incur less risk. If you could deploy things and make sure they work operationally correctly, and then turn on features later, then you're incurring less risk by doing that. And that's exactly what these kind of microservice architectures allow you to do. And this is, in fact, a really common pattern in these microservice architectures, where components are deployed into a production ecosystem, very frequently continuously deployed, meaning that as soon as I've made a change to that code, it has gone through a deployment pipeline and all sorts of testing scenarios and probably some integration testing with some other things. And then it has been put into my production ecosystem live. It still hasn't impacted anything yet, though, because the features are still inside it. So at some point later, you can expose features by turning on feature toggles, which is also quite common in this continuous delivery world. What that allows you to do is run several services side by side with almost identical capabilities, but you still haven't really impacted users yet because applications in this world typically consist of the routing between the services that you have running. And so at any given time, you may have several different variations of a service running and different routes to different services. This is the thing that enables you to do things like A/B testing, which is also quite common in these kind of architectures, because you roll out this new variation and then you have what's called a feature toggle router at the beginning of your application that says, okay, 20% of people get this new feature and let them try that out and see if they like it better, but 80% get the old one. That's really common in this world, that you manipulate applications by the routing of services that they take. And this is the idea of evolutionary architecture I was talking about earlier today, that you have a service, you roll out an enhanced version of that service, and then other services that need that capability can slowly migrate to the new version of that service over time. At some point, no one is routing to the old version of this service anymore. Remember I said part of the workings of this architecture is the operations and DevOps. This is a good example. The monitoring that has to happen in the operations world lets us know when no one is routing to that old service anymore, which allows us to disintegrate it automatically out of the ecosystem. And so this allows us to put services out there and then get rid of them when they're no longer needed, which creates this very evolutionary style of architecture. What this suggests is if you have the right engineering practices in place, the larger the number of services you have, you drive your risk of release down. Because when you're deploying a monolith, it's binary risk. It's all or nothing. It either works or it doesn't, and there's a binary prospect there. But the larger number of services you have, you're displacing less and less of your ecosystem every time. And particularly if you have good testing in place, this actually drives your risk of release down the more services you have. So let's talk about some of these engineering practices that are so necessary to make this architecture work. One of the things that's quite common in this architecture is design for failure. Clients need to respond gracefully to provider failure. We do this through things like monitoring. We're very aggressive about monitoring, for example, like business relevant monitoring. We will look at any sort of business metrics we can gather as part of our deployments and try to monitor those things. For example, we had a client not too long ago that ran a subscription-based business, and they had a monitor in place that said if they roll out a change and the number of subscription reuptakes drops more than a certain percentage, they automatically roll that change back. They don't know that that change caused the problem, but it turns out they like money a lot. And every time the money slows down, they get worried, and so they want to make sure that they understand what's going on to make sure that it doesn't happen again. We also do architectural monitoring. This is this idea of monitoring routes and services to see which ones are being routed to so we can disintegrate them. We also do semantic monitoring. These are things like, for example, it's really common in a RESTful kind of world to have a whole set of integration tests when you have versioned endpoints to make sure the versioned endpoints are getting resolved correctly. We want to take some subset of those development time tests and run them against the production infrastructure to make sure that's still true in production, particularly for critical things where problems pop up a lot, like version resolution for endpoints. We'll take some of our tests and run them against our production infrastructure just to make sure they still work correctly. I mentioned monitoring before. Monitoring, of course, is tricky on a monolith, and it's virtually impossible in a microservices world without some help. Sam's advice here is you have to get much better at monitoring. But what that suggests is you need tools to do this. Many of the things in the microservice world are impractical without tool support. One of my colleagues says it well, that if you're deploying more than 3 services by hand, you've already lost. Because it's not uncommon in these kind of worlds to generate thousands or tens of thousands of monitor trips and log messages a second. Fortunately, there are a lot of good tools to handle this. Tools like Logstash and Kibana let you filter and aggregate these things together and get a nice rolled up picture of what's going on. This is particularly true of aggregating monitors because you will probably want to monitor individual services to make sure you understand their characteristics, but you also want the ability to aggregate those calls together so that you can find out how long a single request, for example, happens through your ecosystem. And so many of these tools support the ability to create a monitor per service, but also an aggregating monitor so you can get the total number of, for example, a request through your ecosystem. Capture metrics and logs for each node and aggregate them to get a rolled up picture is the advice from Sam. Another common engineering practice in this world is synthetic transactions, particularly if you have a basic availability kind of eventual consistency kind of world. You want to make sure that transactional things end up as looking like transactional things. Eventual consistency doesn't mean the transaction is going to show up in a week or two. It means, within a few seconds, but you want to make sure that the end result of that operation is the transaction that you wanted, that, the washing machines that were purchased were in fact purchased and debited correctly. And that's this idea of synthetic transactions. Build into your architecture this kind of a flag where you can flip it and say, okay, I want this to go through and do all the normal processing. And when it gets to the very end, there's a check that says, are you synthetic? And if you are, I'll throw it away. Otherwise, I'll commit it to a database somewhere, which triggers a bunch of other interesting stuff. This allows you to trace the behavior in production of the way transactional behaviors work. So use synthetic transactions to test production systems. This allows you to make sure that the things that are supposed to act transactionally do in fact act transactionally. There's a famous story about this. Be sure that you remember to flip that flag to say this is a synthetic transaction. There was a client who they were running a test and they forgot to flip that flag, and a truck showed up at the home office and started unloading 200 washing machines. And they said, no, actually we don't want the 200 washing machines. That was a synthetic transaction. So be careful that you actually flip the switch when you need to flip the switch. A really common pattern in this world, as I mentioned before, it's quite common to do things like A/B testing in this world. And in fact, the way that you get scalability in this world is you spin up more instances of services. In fact, that's a really common pattern in this world as well, is that you operationally, so services that are going to get a lot of traffic, for example, probably have a built-in input queue. And when that input queue starts filling up, you monitor that and spin up more instances of the service and start spreading out those requests over those instances of that service. And then you can do elastic provisioning and destruction as you need to operationally. But this is where we're saying the architecture really relies on aggressive and agile operations. So what that means, though, is very often if you're doing something, you may go through many different services to achieve the same result because there may be dozens of instances of services running. And you may want to know exactly which service you touched as part of this for debugging or traceability or something like that. That's what correlation IDs are really good for. It's quite common to, as you start a request into this world, tag on a correlation ID, and every one of the services that touch it logs that correlation ID. That allows you in the log aggregation tool to filter for that correlation ID and find out every instance of the service that was hit as that request went through. So this allows you to track down nasty bugs that may exist only in certain kinds of scenarios. Many of you will recognize many of the things I'm talking about here. They're all basically ideas and extensions of ideas from Release It, the book by Mike Nygaard. Things like circuit breakers and bulkheads and timeouts are all good practices in this world from a DevOps standpoint to make sure that things stay up and running as part of this services, microservices architecture. So I said earlier that this is a shared nothing architecture. But then I backed off of that and said, well, really we share two things. And one of them is how all the services integrate with one another. Here's the other one. So let's say that you're in this architecture world and you've encouraged this kind of polyglot world where different people can use different languages, but you have one development team who creates one of these services and forgets to add all the monitoring hooks into it and then puts it live. Operationally, that thing is invisible and has in fact fallen into a black hole. So we need to make sure that we have consistency across services. For example, we mentioned they all need to know how to integrate with one another, but they also need to know how to call other services. How do you discover other services, find out what instances are running? That's going to be consistent across all services. We also need metrics and monitoring and logging and all those things to be consistent. In fact, it becomes a real headache if we can't enforce consistency across all those services. So how can you make sure that all those services share these same technical architecture characteristics? This is where service templates come in. Drop Wizard is a good example of one of these. Spring Boot is another good example of one of these. What this allows you to do is take the shared technical architecture stuff that you want present in each service and kind of snap it into a template. They don't share any of these things across services, but it does allow you to drive consistency across those services. This is Sam's advice. Consider service templates to make it easy to do the right thing. So this is the thing that's owned by a shared services team, and they make sure that everybody uses the same version of the logging tool and the same version of the monitoring tool and enforces that level of consistency. And there's another common use here as well. So one of the usages for that message bus in a service-oriented architecture is to reduce technical duplication. So let's say that you have one service that talks JSON and another that wants serialized Java objects. And that pattern shows up 4 or 5 times in your architecture. In the microservices world, if you really want to be diligent about shared nothing, you'd end up repeating that serialized Java to JSON code in every service, which is not very efficient. What you can do is take that shared code and put it in the service template. That allows you to share it across all services and have a single implementation of it. So you're still coupling them a little bit, but it's really just at the utility level, not at any domain class level. So I think the restriction still applies here. There's absolutely no coupling between domain classes here, but you can use a service template to reduce duplication for those kind of utility coupling like transformations or utilities like XML parsing and other sort of mundane stuff that all of them need as a side service. So let's talk a bit about orchestration. Orchestration is how stuff calls other stuff. And let's talk about 2 styles of orchestration that are common in the microservices world, either choreography or orchestration. We'll talk about orchestration first. So let's say that we have a microservice that's doing an insurance kind of workflow where when we change an address, we also need to recalculate any existing quotes because their quote rate may be tied to their address. We need to update any claims they're participating in, and we need to notify the insured. And there are 2 different ways to handle this coordination, at least 2 common ways to handle this coordination. And one of them is called orchestration, where the front calling service becomes the orchestrator for all the downstream services. So in this case, change address knows, okay, well that means after I've changed the address, we need to recalculate the quote, we need to update claims, and I need to notify the insured that all these things have happened. So this first guy becomes the orchestrator, and it's called orchestration because it's like the conductor of an orchestra. So he's the one that handles all the downstream processing and any sort of errors or other stuff that pop up. The alternative version of this is much more event-driven, much more like an event-driven message queue, much more common in these kind of broker topologies, where each one of these services knows what the next thing that needs to happen. This is a much more publish and subscribe kind of environment where people publish things onto message queues and then services listen on message queues to respond to things. So in this world, change address knows that, well, the thing I need to do after change address is recalculate quote and notify insured, and I'm done. Recalculate quote knows, okay, well, I need to update claims or more likely post a message to a queue that update claims will pick up and then respond to. But in this world, notice all 3 of these send out a message to the notification service down here. Because there's no coordinator to handle this, you might have to build some logic in here to make sure your user doesn't get 3 distinct notifications. Maybe you build some logic in there that says, well, keep notifications for 8 hours and see if I get more than one so I can send a single message or something like that. So coordination logic has to go in a different place here. So really what this boils down to is either mediator versus broker topology, which is quite common in the event-driven architecture world. You see those same kind of patterns in the microservices world as well. So let's talk a bit about deployment and deploying these microservices. One of the things that you don't want to do is force whoever's doing the deployment to understand all the different shapes of all your services, all the different implementation details and libraries, etc. Instead, you want to create a consistent deployment mechanism, whatever that happens to be. Sam's advice here is abstract out the underlying platform details to provide a uniform deployment mechanism. And uniform may be something as cutting edge and as cool as Docker containers. That's become a really popular thing to say, well, we just deploy Docker containers, so put whatever you want in a Docker container. But it doesn't have to be as elaborate as that. It could be that we just run the chef script and it builds up whatever you need to deploy your code. The James Lewis talk that I referenced earlier, that's a purely Java ecosystem, and his consistent deployment mechanism is that every service lives in an executable jar file. And so you just go to that directory and say, run all the jar files, and they bootstrap themselves. They all have an embedded web server and listen on a port. And so his consistent deployment mechanism is just make sure they're all executable jar files. Another piece of advice here is don't let changes build up. There's always a temptation when you have a staging area and you have multiple independent pipelines feeding into that to let things start building up in the staging area. It's like, well, we could put that, well, let's go ahead and put this, well, this is almost done, so let's put, and so you eventually get a bunch of things built up here. You're much better off deploying these things one at a time, particularly if you have continuous deployment in place, particularly if you're doing something like continuous deployment plus feature toggles. Because it's really beneficial to get your things into production as quickly as possible, because you find out if they're going to have any production problems more quickly if you can do that. As long as it doesn't cause problems in your production ecosystem, then it's really nice to get them out there as quickly as possible to make sure that everything works correctly. So the advice here is don't let changes build up, release as soon as you can, and preferably one at a time, and preferably in a continuous deployment kind of world. Another common problem in this world is service discovery. If you have 10,000 services running, how can you find services to do stuff? Well, fortunately, there are tools that help you do this. And in fact, all of the really complex things in the microservices world have tools to make those things simpler. Zookeeper is kind of a general purpose service discovery tool that is broader than just microservices. But both Console and etcd are both tools developed specifically for the microservice architecture space. They will let you create both service-to-service registries and humane registries so that a human can read them and find out what's going on between your 1,000 or 10,000 services that are running. There are service visualization tools. Adrian Crockford, who created a bunch of the cool stuff at Netflix, has released this little open source tool called Spygo. This is written in Google's Go language. These are tiny little simulations. For example, this is a web server, and these are either database servers or application servers bound to them. And this is a way to visualize moving infrastructure around and how things are connected to one another, which is quite common in this microservice kind of space. As I mentioned, there's a lot of tool support needed in this world, and this is a really fantastic resource that a bunch of my colleagues in India put together. This thing called DevOpsBookmarks.com. This is open source tools for all the things in the web and the microservices space. And you'll notice categories over here. We were just talking about service discovery. There are orchestration tools. Provisioning is about machine provisioning, so you can see there are a bunch of those. Security and metrics and logging and monitoring, process management, virtualization and containers, continuous integration and delivery. And you can filter these guys by platform. So this makes a really nice resource to find out, is there some tool out there that can solve this nasty problem? Chances are pretty good that there is. So as I mentioned before, you really need a certain level of maturity before you can create this kind of architecture. This gives you some interesting benefits, but it has a pretty high bit of complexity into it. So make sure that you understand that before you get into that kind of architecture. Simon Brown's a really good, well-known architect in the UK, and he makes an interesting observation here, particularly for people who are migrating a monolith to a microservice architecture, and that is if you can't build a monolith, what makes you think microservices are the answer? Because this is way more complicated than a monolith. And in fact, there is a hybrid between these. I mentioned this morning, this idea of a service-based architecture. You may be struck, as I am, about how starkly different service-oriented and microservice architectures are. They're almost the opposite in many ways. And so what many people end up building now is a service-based architecture. And this is particularly if you're moving from a monolith into a service-based world. And there are typically three changes from the microservice into service-based. One of them is service granularity. Typically you have fatter services here, still with a domain perspective, but much larger in scope than what microservices are. You tend to have shared database scope in a service-based world. This is when it's too difficult to untangle all the transactional context here. And so the service boundaries here may have just become transactional context boundaries. And it's also common here to sneak in a little bit of an integration hub to varying degrees of sophistication here in a service-based architecture. And there's also a relatively easy way to do a migration from one to the other. You start with a monolith, you identify the domain boundaries, you figure out which way to separate those out, you physically separate them, and then rinse and repeat, and you can gradually migrate your way from a monolith into more of a services-based world. The goal here is to partition along natural boundaries, and I've mentioned a lot of these as we were talking along the way. You can go structural with affer and effort coupling. You can go domain-centric using domain-driven design. You can look at transactional context as a way to split things apart. But the best advice here, if you're doing a migration, is build a small number of larger services first. Don't start right away with from going to a monolith to teeny tiny little microservices. There's a great case study about this at realestate.com.au. Sorry, I went too fast on that. From one of my colleagues that talks about how they split teams up in this microservice architecture. That's a good example of Conway's law. Last, how continuous delivery impacts all this. What you really want here are teams that are lowly coupled to each other, delivering relatively independently into a common integration pipeline without fearing breaking each other's bills. That's the goal of microservices plus these continuous delivery practices altogether. That's the last I have, and I think I am way over time. I was supposed to stop at 14:10, so I apologize for that. Thanks very much for coming, and hope you enjoyed it. Thanks.